Okay, welcome to C Programming for Engineers. I'm Professor Miller, and today we are going to jump into our discussion of how computers are organized, and by the end of today's lecture we are going to write our first program. So to start off, how computers are organized, we have different units in the computer. This is a high-level overview. We have input units, output units, memory, arithmetic and logic units, CPUs, and secondary storage units. Input units would be anything that provides input to a computer. This could be keyboards, mice, scanners, pictures, video cameras, touch screens. These all provide input to a computer, and these are our input units. Output units, anything that provides output back to the user. This would be monitors, printers. We also have, for those of you who are gamers, things that vibrate, speakers. These are all going to be output units that we have from a computer. Memory units, now we're going to get into a computer. So on the inside of a computer, we have main memory. And main memory is also known as RAM usually, which is random access memory. Most computers currently are coming with 4 gigs, 8 gigs, 16 gigs of RAM. Somewhere around that is what they come with, depending on how expensive the computer is. They can come with a lot of different memory, a lot of amounts of memory. They are always going to be powers of 2 because computers operate on a binary scale. So we're going to have a power of 2 for how much memory we have, and that's why we use gigabytes a lot of times, megabytes, kilobytes. Those are some of the smaller units. Some of you, after gigabyte, you may be familiar with hard drives. They get bigger than 1,000 gigabytes, and then we call those terabytes. After terabytes, we get to petabytes, and they just continue going up from there. So we're going to continue getting more and more memory. They're going to get larger and larger. One of the issues that we had with memory, though, and we've recently had to overcome that, is that some of you may be familiar now with 64-bit operating systems compared to 32-bit operating systems, and the CPUs that have to be 64-bit instead of 32-bit. The reason that we had to do that is with 32 bits, we had 32 output lines, address lines from our CPU. So let's say this is our CPU, our central processing unit, and we had a number of address lines coming off here, usually 32, that would then go into our main memory. Well, with 32 address lines coming off of this, that meant that each one of these lines could take on a value of either a 0 or a 1. So the total number of combinations that we have of different numbers coming across 32 address lines, where each number can take on a value of a 0 or 1, means that we have 2 combinations for each line and 32 different lines, which is 2 to the 32. Well, if I break this down a little bit, just do a little quick arithmetic here, we can say this is 2 to the 2 times 2 to the 30. 2 to the 2 is a 4. 2 to the 30, if you are unfamiliar with this, 2 to the 10 is a kilo. 2 to the 20 is a mega, and 2 to the 30 is a giga. So we had 4 gigabytes available to us with 32 address lines. That meant that main memory over here was not able to exceed 4 gigabytes if we only had 32 address lines coming out of our CPU. So if we wanted to be able to have more than 32 if we wanted to have more than 4 gigabytes in our main memory, we had to increase the number of address lines that we had coming out of our CPU. So what we've just recently done, maybe in the last couple of years, is up this number from most CPUs having 32 address lines coming out, and most CPUs have 64 address lines coming out. So, looking this up real quick here on Wikipedia, we can see that we went from kilo here at 2 to the 10, and then we went to mega, 2 to the 20, giga, 2 to the 30, teras, 2 to the 40, petas, 2 to the 50, and exa is 2 to the 60. So what we've done now is we've gone to, let's see, the 64 address bits. We do 2 to the 4 times 2 to the 60, which is going to be 16 exabytes that we can address in main memory. Now, since many of us, myself included, have never even seen hard drives that get up to the exabyte scale, I'd say that it's probably going to be a substantial amount of time before we get to main memory, which is in the exabyte scale. Currently, you can go out and buy terabyte hard drives, but that's 2 to the 40. We're talking about something which is still 1,000 times greater than that, just to get up to the petabyte scale, and then 1,000,000 times greater than that to get up to the exa scale. So we're talking about such a substantially large number that we probably are not going to need to bump up the number of bits in our CPU for a good amount of time. However, 32-bit CPUs have probably been around now for at least 20 to 30 years. So maybe in another 20 to 30 years we might need to bump it up from 64 bits, and that's going to be very exciting to see the types of applications that actually need that kind of fast memory access and that much memory in main memory, as opposed to using hard drives or solid state drives or any of the other technologies that we currently have. Okay, the next thing that we have here is the arithmetic and logic unit. This is a part of the CPU. So I've drawn the CPU right here. Inside of the CPU we have a few different parts. One part inside of the CPU is called the ALU. We also have registers. I'll explain those in just a second also. The ALU is the arithmetic and logic unit. This is actually the brains of the computer, and it's very, very simple. There are not very many operations that go on inside of the arithmetic and logic unit. It is the any of the binary operations. So we have AND, OR, exclusive OR, and NOT. Those are the four primary operations that we have for logic operations, binary operations. And then we have arithmetic: add, subtract, multiply, divide, and then we add one more into computers, which is the modulus operator, which is finding the remainder of a division. So there's 5 arithmetic operations, and there are the 4 binary operations. Now, some CPUs get a lot more sophisticated with hyper-threading technology, multi-core CPUs, and so on. Bottom line is that they all are coming down to the same thing, and this is how we compute. We have electrical signals that come into the computer. There's different voltage levels that represent a logical 1 or a logical 0, so we convert them to a binary value. We take those binary values and we do some kind of a mathematical operation on them. We either do an arithmetic operation, add, subtract, multiply, divide, or find the remainder, or we do some kind of a binary operation on it. We AND it, OR it, exclusive OR it, or NOT it. That's really the brains behind a computer. As simple as it may sound, that's really the bottom line. All of the computing goes through the arithmetic and logic unit. What the arithmetic and logic unit is operating on are data from the registers. So we have registers here inside of a CPU also. And the registers, this is the closest memory that we have to the arithmetic and logic unit. It's the fastest. It also is the most expensive. The more registers that you have on a CPU, the more expensive your CPU is going to cost. So inside of the registers, we store the data. It can be numeric data, it can be character data. It's whatever data we're operating on, whatever variable we're trying to operate on in our program is going to eventually make it into a register, so the ALU is able to operate on it. From inside of the CPU also, we have what is known as cache. C-A-C-H-E, cache. There are different levels of cache. The cache is a little bit further away physically from the ALU, so it becomes slightly slower than the registers. However, it's still on the CPU, so it's faster than main memory, which is a separate component inside of the computer, which is connected by a bus. And what that is going to allow us to do is to have more data inside of the CPU, so we have faster access to it, rather than having to go out to main memory all the time and try to pull from there. When we go from the registers to the cache, we have a delay of approximately 10 times of what the speed is as if the data was in the register already. So we want to get as much data into the register as possible. If we can't get in the register, we want to get into the cache. If we can't get in the cache, we want to get into the main memory. When we go from cache to main memory, we have another delay of 10 times. So we ultimately need to get data into the registers to be able to operate on it in the arithmetic and logic unit. If the data is currently in main memory, it's going to take us about 100 times longer to get the data into the ALU from main memory as it would if the data was already in a register. Of course, since we're limited in the amount of memory that we have in the registers, though, we have to play this little game of swapping back and forth between main memory and the registers and the cache and so on. Now, after the main memory, because main memory is not as big as we need it to be either, it's still a finite size. So we have another set of storage devices, which is called the secondary storage units. Secondary storage units usually are drawn like this, and these would be our hard drives. So our hard drives now, I told you we can get up into the terabyte scale. You can buy, I just looked not too long ago, is a 1 terabyte drive. If it's an internal one, you can get it for somewhere around $100 to $150 for a terabyte. If you want an external one, it's still under $200 for a terabyte. Relatively cheap. It's going to continue coming down in the future. And the size of the drives are going to continue increasing. I think I just recently bought a 3 terabyte drive, an external USB one using USB 3.0, and it was something like $220 for a 3 terabyte drive, which is huge in my opinion. But of course, we're going to see applications and more data that needs that storage in the future. Main memory communicates with the hard drive. So as I told you, with the delay that we have from our computers, from the CPU, if the data is not in a register and we actually have to go all the way through the cache to the main memory to the hard drive to get to the data, we're going to have a delay. Well, first from the register to the cache is a 10-time delay. From the cache to the main memory is a 100-time delay. From the main memory to the hard drive is a 1,000-time delay. It's going to take us 1,000 times as long if we have to pull the data off the hard drive as opposed to if it was already in a register. This is a lot of hardware configuration that goes into this. Computer engineers work on this problem all the time, trying to figure out and predict what data we're going to be using in the future, so hopefully we can try to get that data into the registers before we need it. So it's going to increase the time, because while the ALU is operating on data, other things can be going on these components that are independent of it, and they can grab data and pull it into the cache, pull it into the registers, and hopefully we can minimize the amount of delay of having to go all the way out to the hard drive. If you want to see exactly what I'm talking about, just open up like 20 different versions of some program on your computer and then try to switch between one to another. And you're going to notice that there's a delay getting between it. That's because all of this data is trying to get into the CPU all at the same time, and you just have a finite amount of memory, a finite speed coming into your CPU. So that's one way that you can see all of the data processing that goes on. We have one more, it's still considered a secondary storage unit, but we have one more past the hard drive, and this would be if you plug in any kind of an external drive here. External drives are going to operate even slower than your internal hard drives. This would be like a USB drive, popularly called a thumb drive, something like that. This is going to operate even slower than the hard drive because now you're not even on the internal bus, but you're actually operating on an external bus, which is plugged into the outside of the computer. So you can imagine there's another 10-time delay there. Some of you, as you're writing your programs, you may be tempted to use a USB drive. I know they're very popular. You bring them into computer labs, you plug them in, you can save all of your work straight onto it. It's really great. If you try to compile and run your programs from your USB drive, you are going to see a substantial memory hit though. And it's going to run much slower than if you had copied the program onto your hard drive first and then run it from there. Because you have that extra delay of having to go back out to an external device to read all of the data off of it. It's still going to work, it's just going to be a little bit delayed. And as you're compiling and running, and you go back and forth because you're going to do this process countless times for each program that you write, you will notice the difference. And you probably will end up just copying it to your hard drive, running it all from there, and once you're done, then copy that back to your USB drive so you can take it and run it on another computer. Okay, a little bit of an overview of programming languages and high-level languages. A high-level language is a language that is written in something that we can read very easily. Humans can read easily. Typically, we're going to be writing them in English. I have had a number of students who English is not their first language, and they name their variable names and function names in another language, and there's no problem with that. I'll tell you what the restrictions are that we have for naming variables and functions and classes and so on, structures. And as long as you abide by that, you can name them anything that you want. The compiler doesn't have any care whatsoever as to what you name them. It's going to be more of what's meaningful to you as the programmer is going to be how you name them. C was created as a full programming language in the late 1970s. The first book came out in 1978. There have been a number of other languages that have come into existence since then. C++ is a superset of C. It took the functionality of C and added to it, made it even more popular, and added classes and inheritance and some object-oriented programming and so on. For those of you who are going to take the next programming class after this one, you will learn about object-oriented programming. I'll give a little introduction to it towards the end of the semester also, so that you can see what to expect if you do want to take the following programming class in this series. We compile high-level languages down to low-level languages. Low-level languages would be considered assembly language and machine language. These are low-level languages. They are a lot harder to write. There are a lot more lines of code to be able to do something, because we write one line of code in C and it may get compiled down to 10, 20, 30 lines of code in assembly. Assembly language gets directly converted to machine language. So assembly language may look something like, let's move the data that's in register 1 to register 2. The equivalent machine language for that might be a move command is going to be 00000010. Register 1 is maybe 00000001, and register 2 is 00000010. And so we would have these 24 bits would represent this move command right here. And so it's a direct conversion. It's a one-to-one conversion between assembly language and machine language. Obviously, assembly language is a step up from machine. I mean, who really wants to write out all of those zeros and ones to make a program work? And then if something doesn't, you have to go back and go, oh, geez, what is 00000010? What command is that? So assembly language is just a direct conversion. There's no compiling that goes on there, because it's just converting it from a move has these 8 bits, register 1 has these 8 bits, register 2 has these 8 bits, and it just does a straight conversion down. It made it a little nicer for some of the earlier programmers to be able to write their code. However, we have gotten way past that, where we can write high-level languages where we don't need to be concerned so much with the binary aspect and exactly what the operating system and the hardware is doing, but we can write it in a high-level language that looks much more like English. And that's easier for us to understand, it's easier to debug, and then we were able to do very, very sophisticated things where we can have a single command that generates 20 or 30 assembly lines of code, as opposed to us having to manually write all of them and then debug line by line. Okay, typical C program development. We are going to create the program. We usually create a program in an IDE. IDE stands for Integrated Development Environment. The one that we are going to be using in this class is Microsoft Visual Studio. There are other IDEs. You could write it just in a program like Notepad. It's just a text file is all that we're writing, and then you can find command line compilers. One of the more popular ones is called GCC. It's the GNU C compiler. So you could just write the program in any kind of a text editor and then save it just as straight ASCII, and then you would be able to compile it from the command line. You can write it in an IDE like Microsoft Visual Studio. Eclipse has a good one also. You can go to eclipse.org and you can download their IDE. That's a good one. That's actually the one when I do Java development. I use Eclipse as my IDE. For C++ and C, we're going to be using Microsoft Visual Studio. You can download a free version of it online. They have student versions of it. They have evaluation versions of it also. And I also know that the bookstore has them if you want to buy the full version of it. I don't think that it's necessary to buy the full one unless you would really like to. The evaluation copy will probably do just fine, and the free version that you can download online will be just fine for this class as well. After you write the program inside of an IDE or outside of it, depending on how you do it, you need to compile it. There's going to be a button inside of the IDE for compiling it, or they call it building in Visual Studio. If you do it from the command line, you're just going to run another program. It's called a compiler. So there's a program called a compiler, which is going to take your program as the input, and it's going to generate the machine code as the output for it, so that your operating system is able to understand and run your program. Next, we are going to link the program, which if we have other programs that we're going to be linking into it, if we're using other programs, then you would link it there. We probably won't do that much in this class. Maybe towards the end you might write your own program where you do something like that. Load the program into some kind of a runtime environment in the last step, you click the run button to run it, and you're going to run your executable file. It's going to run your program, give you whatever output that you have. Okay, so let me show you here now a real basic program in C. This is how the program looks. This is how we output in C. I've included on this slide line numbers. These line numbers you will not actually type. I've done this just so that I can refer to them and you can know to which line I'm referring as I talk about them. The first line here, pound include angle bracket stdio.h. This is including a header file. This is a library in C called the standard IO, standard input and output. We need to include this library anytime that we're going to do any kind of input or output in C. The second line, void main, this is the name of a function. The function is named main. Void is the return type, meaning that the function is not going to return anything. The parentheses are for passing parameters into the function. Since we don't have anything in the middle of those parentheses, that means that we are not passing any parameters into the function. We open a curly brace here at the end of the line. You see down 2 lines on line number 4 I have a closed curly brace. That denotes the body of the main function. Goes from the open curly brace to the closed curly brace. We will talk in much greater detail about functions in the future. You just have to understand the basic syntax of a C program so that we can get to the meat and potatoes of the program, which is line number 3. Line number 3, we are calling a function called printf. This stands for print formatted. This is how we can output to the user. We say printf followed by an open curly brace. We have our quotation marks here now. Anything that I write inside of this open quotation mark and this closed quotation mark is going to be output to the user. It says hello CSC 205 exclamation mark. That is actually going to be output to the user when you run the program. Close your quotation marks, close your parenthesis, and we put a semicolon at the end of the line. That is the dot followed by the comma. It is on the same key as the colon. It's right next to the L key on most keyboards. So what we are going to do now, I've shown you the Hello CSC 205 program. The first program that you'll see in almost every textbook, every tutorial, everything online that you ever see is going to be a Hello World application. And it looks exactly like this, but it says Hello World instead of Hello CSC 205. I've decided to take our Alaska roots and we are going to write a program instead called Hello Moose. So I'm going to walk you through it from scratch. On your computers, I'm assuming that you already have Visual Studio installed. If you do not have Visual Studio installed, pause the video right now, install Visual Studio on your computer, and then get ready to run it. If you're using one of the lab computers that we have on campus, they already have Visual Studio installed on it. You just need to find it. To find it, we will go to the Start menu, All Programs if you're on a Windows machine, and then we're going to go to Visual Studio. I'm using Visual Studio 2010. It might have Visual Studio 2012 or 2013 on the computers that you're using. It won't have any difference. It's not going to make a difference which one you use. All of our programs will still run, will still compile. So click on Microsoft Visual Studio 2010 and it will, or whichever version you have, it'll open up the program. Wait for it to open. There we go. Opens up. I'm going to move my picture down here out of the way for a second. Okay, what we need to do, all programs that we write in Visual Studio have to be part of a project. So the first thing we're going to do is say New Project. You can either click New Project right here, or you can go up to File, say New, and then click Project. Those both do the exact same thing. It's going to open up a window for you here on the screen. The one that we want to select is the Win32 console application. Do not open one of the other ones. These all do different things. If you want graphical applications, if you're creating a dynamic link library, forms, and so on. These all do different things. What we're going to be using in this class are the Win32 console applications. So click that. We're going to give it a name down here. Let's see, I'm going to name ours Lecture 1. And then say OK. Here's where you can change the location if you want it saved into a different location. what's going to happen is it's going to it's going to create a directory inside of the C:users J Miller 11 documents Visual Studio 2010/projects. It's going to create a directory called Lecture 1 inside of that. If you want to change this and put it somewhere else, you can put it somewhere else. If you want to put it on your USB drive, you can do that. I just caution you that when you're running your program, it's going to take slightly longer if you have it on an external drive as opposed to somewhere on your hard drive. I'd recommend saving it somewhere that you know where it is on your computer, and if you need to access it on another computer, copy that directory to your USB drive and then take that to another computer to run it. So I'm going to leave it right there. I'm going to say OK. And here we get an overview. This all looks okay. Click on Application Settings. Make sure that Console Application is set. I'm going to click this checkbox here that says Empty Project. I want Windows or Microsoft Visual Studio to generate the least amount of code possible. So I want a console application. I want it to be empty, and then I click Finish. And at that point, we should see over here in our Solution Explorer that we should get our Lecture 1. So there is our project. We have some directories down below. We haven't done anything yet. We can't start typing code yet. The next step, we're going to right-click on Source File, say Add New Item, and click C++ file .cpp. I told you anything that you can do in C, you can do in C++. So we're actually going to be writing a C++ file, although we're going to be using the syntax for C to do it. So click CPP file right there, or C++ file, which is a .cpp extension. Down here where the name of it is, name it whatever you want. It doesn't matter what you name it. I'm going to name mine Hello Moose.cpp, and then click Add. Now we get this nice text area here in the middle. You see it's called Hello Moose.cpp, and I can type code into this window. Whatever I want to type, I can just put right here. So I showed you the code already. We're going to kind of copy it. We're just going to change what the string was inside of that printf statement. So the first thing we do, pound include stdio.h. We're including our standard io.h header file into our code. Okay, so I made the font a little bit bigger. Hopefully you can see that a little better. So there's the pound include stdio.h. And now we need to have our main function. The syntax of the main function is void main, parenthesis, parenthesis, and then you open up your curly brace, go down a couple lines, and close your curly brace. Everything that's inside of the curly braces is called the body of the main function. So inside here is where we're going to add our printf statement. We say printf, open your parenthesis. You see that a little tooltip pops up there. That means that you're doing something right. Open your quotation marks, and then here is where we are going to type whatever we want output. We said that what we wanted to output was hello moose followed by an exclamation mark. So you type hello moose, exclamation mark, close your quotation marks, close your parenthesis, put a semicolon at the end of the line. That is all there is to our first program, hello moose in C. After you type that, go up, click the save button, save hello moose.cpp. Now the next step is we need to compile it. To compile a program in Visual Studio, you go to build and say build solution. When you do that, you see down here at the bottom of the screen, it says build started, it's building it, it's trying to compile it, and if it succeeds, you see that you get that line right there. It says build succeeded. That means your program compiled, there were no syntax errors, and you're ready to run it. To run your program, you go up to build, say start without debugging, and when you run that, this little thing pops up, and you see right there it says hello moose exclamation mark. That's our program. You see it succeeded. After that, it says press any key to continue. You can just hit any key and it'll close that window. I know it's very exciting. Make sure that you go show your parents how exciting it is that you wrote your first program that said hello moose. You can now change this, make it say whatever you want. It doesn't even have to say hello, it doesn't have to say moose. You can make it say anything that you want. You can type it right inside of those quotation marks. You run your program again and it's going to print it out just like it did before. One question that you all may have right now, this looks a little kludgy that you see that it says it hello moose exclamation mark, but then there's no space or anything here. It just says press any key to continue. If you want to fix that right after the exclamation mark, put a backslash in. Backslash in is a special character in C. In a lot of programming languages, it works in C++ and Java also. It stands for a new line character. Put the backslash in right after the exclamation mark. The backslash is right above the enter key. It's on the same key that has the pipe on it. Make sure that after you make any changes, you have to save it, compile it, make sure that it still compiles, and then you can run it again. And now you see that I have a nice pretty output where it says hello moose with an exclamation mark, and then on the following line it says press any key to continue. And then when I hit any key, it will close that window for me. So there's your first program. Hopefully you enjoyed writing that. You all followed along. You can go back through the lecture. If you didn't quite catch everything, run it again and make sure that it works. Last thing that I want to do right now is go over your assignment 1. I will do that in the very next lecture right now, and you can get started on that, which is going to be due next week. So start writing code, look through the book, ask me any questions that you have, and I will see you guys in the next lecture.